All right, questions about the menu?
That's the last problem. That in the second classes, online classes. Yeah, and after that, they I need to graduate with physics or like.
Let me check. If anything doesn't show, just send me an email. Make sure you put 2120 though in the subject, because I get so many. What?
Because it gives X2 of Z, and then it just, and the
Is that, was
solution
it
bar.
with Quizzoto or, okay, yeah.
The X2 of them.
Yeah, yeah, everyone, that's one of everyone's least favorite classes to go through. I didn't mind it, but yeah, that's okay.
For one?
No. For intermediate. Yeah. He is, yeah. I thought it was an interesting class, but yeah, he didn't make it very exciting.
Well, you can tell what X2 is just by looking at X2 of Z. It's 1, 1, 1, 1, 1, 1, 1. Take a look at that. Let's see the coefficients is Z to the minus 1, Z to the minus 2, Z to the minus 3. They're all 1s, so it's just straight 1s out to from 3, 4, 5, 6 of them. You see that? So that would be that's the second part of that one. Anyway, you know, convolution, the whole deal is you do it in the, you go ahead and do it with the Z transforms, multiply them, and then do the inverse if they want. Speak of that, yeah. All right. Did you have a question about any of anything that needs to be worked? Did you do it? All right, I'm going to go through any questions at all about the Z transforms, because we're going to start applying them to things, or applying them to actual difference equations and then getting the general transfer functions. First, I mean the transfer function, which is the impulse response of the system, and a few other things. I'm going to talk about getting the inverse Z transform and going through it with you. If you've read the book of this, you can see that there are really a couple of ways to do it. A lot of it parallels to Laplace, though. The way we did with Laplace transforms, we did partial fraction expansion, and we calculated the coefficients using the cover-up method. It's the same with this. There's a couple differences, though. First, I want to say, in general, when you have a system and you have some difference equation, then you're going to have some H. Get rid of that marker. Is there a wastebasket anywhere?
No, if you can throw it to me and I'll throw it away on the way out.
I'll just throw it down there. I'll take care of it. In general, let's see this works. If you have some H of n, you know that goes to an H of Z. Now the H of n would be the impulse response to the system. In other words, a difference equation would have a ratio of output to input, which would be H, what really is going to be an H of n, basically. Now, when you have this, how do you get the inverse so you can actually find out what H of n is? I'm going to say, suppose you have a difference equation, you get an H of Z, but you want to know what H of n is. So suppose I have, and I'm going to come up with just some examples. I have H of Z equals Z to the minus 1 over, I'll make this Z squared. Make it Z squared minus 1 over Z cubed plus 2Z plus 4. Now, look at that right there. A couple ways to figure out what the actual values are, to get the actual value of H of n, or solve for H of n. I'm trying to say this in a way that's not confusing. Doing it, which is called the direct method, by doing dividing the actual denominator into the numerator. So I'll do this here. If we took Z squared, look up here. If I take Z squared minus 1, And now I go ahead and divide into it z cubed plus 2z plus 4. If you look at this, you look at the highest powers, cubed goes in the squared, 1 over z, or z to the minus 1. Do you all see that? So you put z to the minus 1 here. And I might add, there's a couple other tricks I could do, but for now, I'm just going to do it this way. So now I multiply through by that, and here I'm going to get z squared, right? Then I'm going to get plus 2. Then I'm going to get plus 4z to the minus 1. Take a look at what I've done there. Just multiply z to the minus 1 by that. Everything's reduced by a power of z. Agree, class? Now you subtract them. When we subtract these, it's basically changing signs and adding, right? So I got z squared from z squared is 0, plus, then I've got minus 1 minus 2 is minus 3. Then I have minus 4z to the minus 1. Y'all agree with that? Just keep watching, you're going to see this. So the next thing I do is see that the highest power that's left is minus 3. So z cubed goes into minus 3, minus 3z to the minus 3 power. Do you all see that, class? So it's going to be minus 3z to the minus 3 power. And when I do that, now I'm going to go ahead and get minus 3. Then I'm going to get minus 2z to the minus 2. And then I'm going to get minus, I'm sorry, that's wrong. I did that wrong. This is going to be minus 3. Then it's going to be minus 6z to the minus 2. And then it's going to be minus 12z to the minus 3. Then I change that signs and add them, right? That's a simple way of thinking about it, so I go and just add them up. And here I get 0. And then I'm going to get plus 2z to the minus 2 right there. Now take a look at that. That would be plus 6z. 6z to the minus 2, and then it's going to be minus 4z and plus 12z to the minus 3. Are you with me on this? I'm going to just show you one thing I'm going to add up here. If you're looking at this, what you're seeing is something that's, I'll tell you it's important. When I look at this function h of z, what I know it is by definition is a summation from n equals here, it's going to be 0 to really infinity of x of n z to the minus n power, which means really it's x of 0, and then it's going to be plus x of 1 over z, or times z to the minus 1, maybe I'll put it that way, times z to the minus 1. And then it's going to be plus x of 2 here, z to the minus 2, plus x of 3, z to the minus 3, plus, and so forth. Do you all see that, class? I'm just writing out the term by term. Well, if you look here, there is no constant up here, right? Y'all agree with me? So I can put this 0 plus that. I'm going to do one other thing. I can see actually that I have plus 0z to the minus 2 here, don't I? And then I have 0 times that minus 3z to the minus 3. Agree? Follow me on this, guys? Y'all see what I'm writing here? I added the 0 on purpose. Why? Because 0 is x0. Just put it down. This is x0. It's 0. x1 is the coefficient of z to the minus 1. Can y'all see it's 1? So that's 1. So x1 is just 1, right here. x1 is 1. x2 is 0, right? x3 is minus 3. Y'all see what I'm doing? And now we're doing by a direct, really just long division, we're calculating the values of all the values. Really, this is h, I put it as x, but this would really be the h0, h1, h2, and h3, and so forth. And you can go on and keep doing it this way. That's long division. MATLAB has a command to do this. If you actually look on MATLAB and you have an h of z, and you want to get h of n, or you basically want to do long division to get the actual h of n, or any function. If you have any x of z and you want x of n, it'll do the inverse for you. There's a z transform, it's called z-tran, and then of the function of n, and if you want the inverse, it's iz-tran. And you can put the function of z and it'll do that. And I'll do that for you. Do you have MATLAB on yours?
I locked it, yeah.
Take a look, just type help and then put z-tran, and it'll show you the commands for this. And I'll give you some examples. Now the reason I'm doing this for you, I'm doing with long division, is that's what MATLAB can do for you very quickly. You can get all these values. Now you can see that this may be a long thing. It may be drawn out this way. Do y'all see that? It may go on for a long time, which you don't want. But this is one way of getting the inverse z transform. It's by long division. Everybody agree with me? The next way, I'm trying to show you as many as I can, that we do is really just like the plots. Remember, we had simple poles, then we had repeated poles, we had complex poles, right? And the way we always did that was with partial fraction expansion. Well, you can do it, you can do that too, but I got to tell you one thing that's almost always necessary. Whenever you have a function and you want to get the inverse z transform, normally, if you have x of z, what you need to do is divide it by z first. Now, if you think of the normal transform pairs, just for a second, and I'll tell you what. Suppose I have just like a to the n, u of n. What does that render? Isn't that what? Z over z minus a is one way of writing it. Do you all agree with me? Mm-hmm. Well, you all see that this isn't going to lend itself easily to a partial fraction thing. If we divide by z first, right? If we divide that by z first, then the partial fractions become easy to do. That's the reason you divide by z first. It'll make the partial fractions easy. Then when you get the partial fractions, then you just multiply by z. All right? And then you can get the inverse z transform. And you'll get a lot of stuff like this, simple stuff like that. Anyway, so now, if I want to take a look at a problem that, and I wrote this thing down last night when I was going through some of it that I thought was fairly typical. This one's going to bother you a little because you're not used to seeing this kind of factor, but I'll take you through it. Suppose I said my x of z here, before I divide it, is going to be equal to 6z cubed plus 2z squared minus z over z cubed minus z squared minus z minus 1. Well, the first thing, when I take a look at this, order of the numerator is the same as the order of the denominator, which means it's an improper fraction. This is not going to be one you can do a pole expansion without dividing by z first. Y'all see that? So I divide by z first, and when I do that, I can do it here. That becomes squared, that becomes z, and that becomes 1. Agree? Now, this is one of those you don't see this often. If you get a z minus 1 out of here, you see how they have descending orders of z? You have cubed, squared, single, and then constant. If I see the first value and the last value, if I just factor out z minus 1, this is, I know there's no coefficient in front of there, and I see the last value is minus 1. If I factor z minus 1 squared out of there, it'll probably work on this one, just by experience. So if I just take a look at this, if I have z minus 1 squared. That's z squared, right? And then it's minus 2z plus 1. Y'all agree with that? This is one, it comes from just experience. If I take that and I multiply it by z plus 1, then what do I get? Now I get z cubed, right, minus 2z squared, and then plus z. Then I have plus z squared minus 2z plus 1. Agree? Yes, miss?
You're doing that to make the partial fraction?
I want to show you that this z plus 1 times z minus 1 squared is that. This isn't an easy one to see. Let's see if it is. See if I'm right about this. All right, when I look at the highest powered z cubed, do you agree with that? Z cubed. What's the next power? I have minus 2z squared plus z squared, so it'd be minus 1, right? Follow me what I'm doing? And then with z, I have what? I have plus z minus 2z, or really minus z, right? And unless I messed that up. Oh, this should be plus 1. My bad. It should be plus 1 then. And it is plus 1. And in fact, I'm bad on that one. This is the way it goes. Now, the truth about these are, this type of factoring is kind of tricky. Anytime I see a z, I've got a highest power coefficient of 1 here, and I got something back here, the tail end of that, almost always it's going to be this minus the last part squared for starters, and then it's going to be times something else. But I don't expect you to know how to factor these things easily. I'll take you through some of them. I've chosen this one just because it actually has the double pole and the single pole, and that's the reason I want it. So now, if I take a look at this, and these are the factors, now I can say that this, in fact, right here, if you don't like this, I understand, because this is a little tougher. If I have x of z over z, I know it's going to be equal to 6z squared plus 2z minus 1 all over z minus 1 squared times z plus 1. Y'all give me that? Agree with me? Now you can see for this one, we've got a double pole and we have a single pole, right? Remember, it's divided by z. So for the single pole, I'll just take c0 over z plus 1. And for the double pole, you have to go c1 over z minus 1 first, right? And then plus c2 over z minus 1 squared. Now, do you remember how to get these from Laplace, everybody? How do we get c1, or c0, first one? Just tell me. Where's the pole at? Z equals minus 1. So normally we cover this up, right? Right? And we evaluate everything left when z is equal to minus 1. Do you agree with me? So if we do this for c0, you guys can do this. It's going to be 6 times minus 1 squared, or 6. And then it's going to be minus 2, minus 1, right? Downstairs I have z plus 1 covered up. And z here is going to be minus 1. So I have minus 1 is minus 2 squared is 4. And I can see here I have 6 minus 3 over 4 or 3/4 for c0. Do you all agree with that, class? Right? All right. Now how do I get c2? Say again? Well, for this one, because this is the highest power of the pole, right? Now I can cover up the z minus 1 here, right? Right? Z minus 1 squared, correct? And then I let z equal to what? 1. And what do you get? I get 6 on top plus 2, right? Or 8 plus 1 is 9, correct? And then it's divided by what? 2, is it? Can you all see that?
But isn't it 6 plus 2 minus 1? So it can be 8.
I'm sorry. I have, for this one, z is equal to 1, so I'm going to have 6 plus 2 is 8, minus 1 is 7, you're correct? And then downstairs, I'm going to have divided by 2, so I'm going to have just 7 halves, correct? So then I can say C2 is equal to 7 halves. How do I get C1? Anybody remember?
Divided by z minus 1.
Anybody? There's two ways to get it. What is a common denominator? You all remember that? You put everything under a common denominator over here, correct? And since we have C0 and C2, getting C1 shouldn't be that much trouble, right? What's the other way? Do you remember? Who's talking? You said?
You match up the numerators.
Well, that's getting a common denominator, equating coefficient.
You have the.
Multiply by what? Z minus 1 squared, right? And then take the derivative. Do you remember that? So I'll do that over here just to show you. We'll do if you want to do the common denominator one, we go too, but I think we'll do that one too, but let me do this second one. So if I wanted to get C1, I'd multiply this here, that's supposed to be a square, multiply that by Z minus 1 squared and take the derivative. So I have to take the derivative with respect to Z of 6Z squared, right? Plus 2Z minus 1 over Z plus 1. I have to take the derivative of that and evaluate it at Z equals 1, correct? At Z equals 1. And this would be equal to my C1. Do y'all remember doing this class? Yes.
Minus one? That's minus one.
We're finding C1 and Z.
See, we're multiplying through by this pole, Z minus 1 squared. That's when Z is equal to 1, isn't it? 1 minus 1 would be 0, correct? So I multiply Z minus 1 squared over here, then take the derivative, right? Y'all remember this is the one trick of Laplace we had to do to get it? When you take the derivative of that, what do you get? Well, I'm going to take the derivative of the top times the bottom. So the derivative of the top, C1 would be equal to what? It would be 12Z, right? Plus 2 divided by Z plus 1. And then it's going to be plus the top, which is 6Z squared plus 2Z minus 1 times the derivative of the bottom, which brings out a minus sign, and it's Z plus 1 squared. Y'all agree with me? Right? What's this going to be when Z is 1? Just take a look at this. I've got 12 times 1, right? Or 12 plus 2 is 14, divided by 2 or 7, right? And then what is this one going to be? Minus the quantity. I got, what, 6 plus 2, right? Or 8, minus 1 is 7, correct? And it's divided by 4, right? Do you agree, class? So I'm going to have minus 7/4. And what is that going to be? Well, that's what? 28 minus 7/4 or 21/4. Isn't it, class? Is that right? Class? So that would be C1. That way. And you can put them in. And then to get the I'm going to do it this way. And what the other way to do it is what? Equating, or really getting everything under a common denominator, right? So I have to take C0 here, right? And I have to take it times Z minus 1 squared, correct? Then I'd have to take C1 here and take it times Z plus 1 times Z minus 1. And then I would have to take C2 and multiply it by Z plus 1 all over this, Z minus 1 squared times Z plus 1, and then equate coefficients. Agree, class? How many remember doing that? It's kind of it's tedious to do that way sometimes. I prefer doing it this way. Anyway, regardless of the way you choose to do it, now when we go back to this thing, I'll put the values in. C1, or C0 was 3/4, right? I'm going to go ahead and put it in. We're going to do this one entirely. What is C1? 21/4, right? And C2 was 7/2. Y'all agree with me? Anybody guess the next step? We're almost there.
You just bring the Z back over and then inverse.
Multiply everything by z, correct, class? So when you multiply it again by z, I want us all to do this one. Now I have z on top here, z on top here, and z on top here. And now we go ahead and take a look at what the inverse is. First one I'm going to do is this one. You recognize that one? I'm going to put them over here. I want to put the pairings up. Y'all remember if you have just u of n, that goes to, that's like a of n times u of n, and where a is 1, right? That's just what? Z over z minus 1, correct? Now, if there's a coefficient of 5 here, coefficient of 5 here, if I look over here, my coefficient is 21/4, right? So this one going back is what? Into the n domain. It would be 21/4, guys, times just u of n, isn't it? Agreed? All right, what about this transform? What does that look like? Let me do it this way. If I have minus 1 to the n, u of n, right? Now, note this, people. Please just pay attention to this. This minus 1 is a. Remember that. It's like a to the n u of n, right? So that goes to what? That is like z over z minus a, correct? But if a is minus 1, it becomes
Let's say.
plus 1, right? So this is plus 1. You agree with me, everyone? I'm showing you this for a reason. Believe it or not, stumps people on tests. I promise you that does. So now coming over here, what does this one go to? 3/4, come on. Z over Z plus 1 is minus 1, right? To the n, u of n. You all agree with that? Right? Keep going. What about this one? Final one. I mean, let's do this. Remember, if I have a to the n, u of n, that goes to z over z minus a, right? Or it can be written as 1 over 1 minus a z to the minus 1, right? Either one. Now what happens if I have n times a of n, u of n? People. Now it's going to be what? Minus what? Z times, right? Derivative with respect to z of z over z minus a, one way to write it, or just derivative of that. Do you agree with me, class? Take a look. Isn't that a property? Please take a look at this property. It's a very powerful property. Y'all see that? If you have n, really the property I'm talking about is n times x of n here. Look at the properties. That's minus z times the derivative with respect to z of x of z. Isn't it in your properties? Just take a look there, people. You got your properties over there? We actually proved this the other day. You remember? They have it in this form, minus z times the derivative with respect to z of x and z. All right. So we can see from here, what does this become? Minus z, right? Well, derivative first is 1 over 1 over z minus a, correct? Plus the first, which is z times the derivative of the second, which brings a minus sign, right? And then it's going to be z minus a squared, correct, class? Isn't that it? Now, if you go ahead and get a common denominator, now I have z minus a, right, minus z, correct? Or times the z out front. So now I get simply, it's going to be minus z times the quantity, z minus a minus z, or simply minus a over z minus a squared. And the minus signs go away, and therefore this becomes just ZA. Now, the reason I put it that way is now look over here to this one. The 7/2 you ignore. This is the one you want. Take a look at that and that. What is A? 1, right? Y'all see that? So what happens over here? I have N times U of N, don't I? Does that have that transform in your book, by the way, N U of N? So that's plus 7/2 times N times U of N. Y'all agree with me? Now, believe it or not, that example exhibits the 3 basic problems with this type of stuff. Complex, I mean, I didn't get complex poles, but it's got a single pole. It also has a pole where the root here is at -1. It's going to have a pole where it's not just a normal z minus like 1 or minus a half or something like this. You got z plus 1, and you got a double pole. And if you look at this, this is something that's flipping back and forth from positive to minus continually, right? It's just 3/4, and it's either positive or -3/4. It's like a sine wave. Think about that. And in a sense, it's just what? Same magnitude, it's opposite signs every time you add in, right? Plus, minus, 3/4. This one is a constant. It's DC. It's 21/4. It's U of N. And this one here is exponentially growing. Do you all see that? Take a look at that. N U of N. Follow me? Add all those things up. You've got the impulse response. Does anything bother you about this right here? Where does that value go as N gets very large? Infinity. Does that sound like a stable system? No. If the impulse response is not finite, as N goes to infinity, it's not stable. I'm just telling you that right now. So this wouldn't be stable. We'll get to that with the actual region of convergence business in a bit. But I want to make sure you saw that too. Now, and I love what you something. When we do, see, complex poles is not something you can do for Z transforms without a calculator. I don't allow calculators on the exams. So generally, I don't worry about complex poles with Z transforms. I can show you how to turn these into sines and cosines in a bit. But for now, don't worry about the section of the book that does complex poles with Z transforms, all right, at all. Because really, then you're going to get 2 poles where the actual poles are conjugates. They're complex conjugates of one another, but don't worry about that. That's not something that is that important for this discussion right now. Now, if we did an inverse Z transform, I'll give you some of them to do, and I'm going to tell you one thing. If you have any problem factoring these things, MATLAB has a routine that you can use to factor. If you have a series of numbers, and it shows you how to put it in there, so you have z to z cubed minus 2z squared minus z plus 5, something like that, and you want to see if it can factor nicely, MATLAB has a routine to do that. I'll give that to you. You don't have that on the test, and I don't ever give you things that are tough to factor on the test. That one I'd probably give you a hint on, because I can see right there that you're not familiar to doing that, right? But simple ones I don't. Now, next, applying Z transforms to actual difference equations and then getting meaningful results from transfer functions. So I need to tell you one thing before I get going. You've been exposed so far to analog circuits, right? I don't want you to write anything, I want you to just listen. If I have a circuit like this, where I have an input, call it X of T, a voltage, and I have a resistor R, say an inductor L, and I have a capacitor C. And I want V out of T. For any input X of T, if that has a value of L and that's C, then based on your understanding, let's assume there's no initial conditions of Laplace transform. You can use Laplace transforms and easily give me the transfer function, first of all, the relationship of output to input. Do you all agree with that? Matter of fact, maybe I should call this Y. You don't write this down, just listen to me. If I did this with a transfer function, and I want to make sure you see this, I could say that this impedance is R, this impedance is SL, and this impedance is 1 over CS, right? And if I want the ratio of output to input, I could write H of S here, or H of S, as simply what? As simply 1 over CS, right? Over 1 over CS plus SL plus R. That would be a transfer function, right? I could also write a differential equation that describes the relationship of current to voltage in the circuit. I know if I assume of I of t here, the voltage here is simply I of t times R. The voltage here would be plus to minus L times di dt, right? That would be the voltage across the inductor, assuming current is known. And the voltage here would be, really it'd be what? 1 over C, the integral, really from 0 to t, and then it would be I of t times dt. This would be prime. And you could go ahead and write a differential equation to describe that circuit operation too. Do you all agree with me? I'm not going to go ahead and do it. So I could do it from when I do this analysis, I could go right to the Laplace domain by instinct, right? You know how to do that. Or I could write a differential equation and solve the differential equation. But in other words, I have everything I need to know to find out the output voltage for any definable input voltage in terms of a function. If it was u of t, the Laplace transform would be 1 over s times the h of s, right? If it was e to the minus 5t u of t, this would be 1 over 5 plus s, right? And we could go through just the innumerable numbers of input-output. You've got everything in your toolbox to analyze an analog linear time invariant system. In other words, from input to output as engineers. Got it, guys? There's no amplifiers that could put an op-amp in here if I wanted to, and you could do that too, remember? But now you've got it. Now with digital circuits, or with circuits that are now going to be, I use the word digital loosely, but they're going to be something where we're going to have difference equations that describe them, Z transforms that are likened to the Laplace transform. This is the way it's really done. Now we're going to have digital circuits phenomena that we're going to be modeling. I mean, we're not quite there yet, but we're getting there. We haven't talked about quantization here, and we may not, but that's something that's the last step in this thing. But we're talking about now taking sampled signals, right? And now instead of a differential equation, you get a difference equation. I'm going to do this one time for you. I want you to just watch this. You don't need to write this down. This is an analog circuit that shows you've got all the tools to do that. Now, if you think about a standard differential equation, dy dt plus ay equals x. These are functions of time, x and t, right? Now, if we looked at that from a difference perspective, the difference between the values, a derivative would be the difference between one value and the next value divided by a delta t. So this would be like y of n minus y of n minus 1 over some delta t. Follow me? The delta t is just some arbitrary time step. Do you all agree with that? That would approximate a difference between the two, and it'd be like a differential equation. Plus ay, it would be times a times y of n here, is equal to some x of n. This is a difference equation. You'll notice that the delta t there really is something that you probably should multiply through everything by. And I'm going to do that. So now your difference equation would look like this. And I'll just call it delta t a here and delta t x of n here. Can be anything. Right? Delta t is an arbitrary value. It can be 0.1, it can be 1, it can be 5,000. Doesn't matter what delta t is. But that's a difference equation that is identical in terms of what it does to the difference, or to the differential equation. This is a difference equation that's identical to the differential equation. Now we're in discrete time. This is called a difference equation because it is the difference between values of y and x that are important. Now we can get a z transform for this. All right? If we get a z transform for this, we get y of z, right? Minus, and what is this one going to be? It's going to be z to the what? Minus 1 times y of z, right? Plus what? Y of minus 1. Take a look in your book. Do you remember that? For the actual, This is gonna be what? The property where we have, the transform of y or x of n minus one. Do you all see that in the book? Do you remember? All right, now I have to put this in brackets here. Plus, this is a constant value, but I'll call it a delta t times y of z here is equal to delta t times x of z. Now you can almost see what I'm up to. I'm going to factor the y of z on one side, the x of z on the other, right? And then I'm going to get the ratio of y to x. Do you all agree with me, class? Output to input. And when I do this, what do I get? Well, how about I make it easy on myself? I'm going to say y of minus 1 is 0. There's no initial energy or initial conditions. This is more or less just to show you with a difference equation how it is akin to a differential equation. And it's the simplest one. So if that's the case, I can get rid of this, which is nice. And now, when I go ahead and group things, what do I have on this side? I have what? Y of z, right? Then I have quantity 1 minus z to the minus 1, right? And I have plus a delta t here times y of z is equal to delta t here times x of z. Do you all agree with that? Now I need y over x, don't I? What is that going to be? When I take y, that's called the h of z, the transfer function. H of z is going to be equal to, take a look at that, y of z over x of z, right? Y of z over x of z is going to be delta t over, and then it's going to be,
The other way, when delta t be on the bottom?
I couldn't hear you.
Would delta t be on the bottom or the top?
Well, you're dividing everything by delta, everything by x of z. So this is y of z over x of z, and this is going to be delta t, and it will be divided by all that. Right. So that would be delta t over the quantity, and then it would be 1 plus a delta t here, and it's going to be minus z to the minus 1. Can you all see that right there? Everybody? Now, the thing I really should point out, this 1 minus a delta t is like a constant. The delta t is like a constant. Do you agree? I'm going to make it two different constants. I'll just call this one a, and I'll call this one b. Doesn't matter what they are. Agree? Now remember, that is h of z. If I go ahead and multiply the top and bottom of that by z, now I have b times z over 1. I have az minus 1, right? And then if I divide top and bottom by a, you'll see where I'm up to. Now I have something that looks like it can get the inverse transform of fairly easily. Do you see how this looks like z over z minus a? 1 over a, right? What's the inverse transform of that going to be? That would be b over a, this is going to be the inverse of that, times what? 1 over a, what? And u of n. And that would be the impulse response of that simple difference equation. Understand, class? That's it. For a simple difference equation. Now you can almost see where I'm going with this. Now, when we're dealing with circuitry, think about the way you've learned. You know how you have clocking periods, right? And everything pushes through. Where I'm going to have values now, I'm going to push through x of n, x of n, all right, we call it x of 0, x of 1, x of 2, x of 3 that I'm feeding in. And now I'm going to go ahead and operate on that with different things where I take the value of x of n minus x of n minus 1 to give me some value, say y of n, all right, and where I could add them, or I could do anything I want, but basically now I'm going to be combining sums and differences with multipliers to get an output relationship, maybe n different outputs. Maybe not just y, maybe I have y1, y2, y3, y4, and a whole bunch. But they're based on clocking the circuits. Basically, I'm going to feed the inputs, x0, x1, x2, x3, x4, and I'm going to be getting outputs, y0, y1, and it's in real time. Follow me? Just like a differential equation describes the input-output relationship, in real time of a linear time invariant network. You follow me on that, guys? Right? Same with this deal. It does. So, now we take a look at actual systems of differential, or of difference equation, find the h of z, and then do the analysis just like we would do it in the Laplace domain. And, I mean, you've done this kind of stuff before, so I want to do it now. You have your book with you, right?
Yes.
Take a look at the back of that chapter, where it has back to the Z-transform chapter. Sorry, there's, take a look at the problems. Just give me 1 second on this. Trying to do one thing before I go. I have some overheads, but I prefer not to do it.
Page 415.
If you look at problem 734, right there, 735 and 736, he has difference equations, if you look there. Just take a look in your book. I'm just going to, I want to put this up generally. Let's do, was 734 the first one at the top there?
Yeah.
Give me 1 second on this one, please, class. Go ahead, give me the first part.
So your x of n equals 9 plus 2 cosine,
X of n equals 9 plus, go ahead.
2 cosine pi over 2 n plus 3 cosine pi n.
Go ahead.
And then you want 5 times y of n
5 times y of n, go ahead.
plus 3 times y of n minus 1
Go ahead.
plus y of n minus 2 is
Right.
equal to 7 times x of n plus 7 or 6 times x of n minus 1 minus x times or x of n minus 2.
N minus 6?
2.
2. Now, I want you to just look at this for a second. Before you focus on this, you realize we can get the Z transform of each one of those very easily. Follow me on this, class? That's very doable. Down here, can't we get the ratio of x to y here? And by the way, doesn't he have this as a u of n here? This is for n positive, n greater than or equal to 0? Well, he has to, or else this problem will make no sense. This should have times a u of n here. This Z transforms that we work are only for n 0 or greater than 0. All right? So it just means this thing turns on at n equals 0, and from there on. There is no n x of minus 1, x of minus 2. Follow me in this class? Please listen to me. Now, y'all see here, assuming that this turns on at n equals 0, there is no value for x of minus 1, x of minus 2, x of minus 3. Follow me on that? They're all 0. Got it? What that means is when we have these differences here, their y of minus 1, y of minus 2 will also be 0. Now that's not said explicitly, but this is important. So just do the Z transforms of this for 1 second. Let me finish this before I let you go. What happens here? I have 5 times y of z, right? Assuming the y of minus 1, y of minus 2, all that business is 0. What happens here? Plus 3 times z to the minus 1 y of z, correct? Forget the y minus 1, right? What about the next part? Plus z to the minus 2 times y of z, right? Equals 7x of z plus 6z to the minus 1 x of z minus z to the minus 2 x of z here. Agree, class? Y'all agree there? Y'all see you can multiply this whole thing, the equations, by z squared. And then your highest coefficient here would be z squared, z, and 1, right? Same here, you would have a z squared, z, and 1 here, and then you can get the ratio of y to x. Did you all see that, class? Now, once you have the ratio of y to x here, you have h of z, don't you? Once you have h of z, if you multiply by the transform of that right there, you in fact have what? Now you have the output, correct? Y of z. And if you do the partial fraction expansion of that, now you can get, you have to divide by z first though. But then you can get the actual output. That's what I was trying to get to today, and I ran out of time. But you can do this. I'll send you this stuff. Somebody's gonna send me, what about Friday, a quiz? We'll do a quiz on basic Z transforms, all right? How about, I won't worry about the inverse to squared transforms, all right? But I want you to do this one, okay? Is there a test today, Sean?
I had one this morning.
You have one coming up?
No, I had one this morning.
You have it? We're missing people today. I don't know how many, but so.
It's nearing the drop date.